This is also a 2-scale diagram on the surface of the Earth. This is a cross section of the Earth. And we're gonna reenact the example given in the Navy video called Navigation by Lighthouses, Night Piloting, 1943 US Navy. So we have Cape Charles Light, a focal height of 180 feet, distance 15.4 nautical miles to the horizon. I've marked here the theoretical horizon at 26.4 kilometers. But the naval manuals claim 15.4 nautical miles horizon, which is marked here with the orange arrow. We have an 8.5 nautical miles distance to the first ship, and we have another 2.4 nautical miles distance to the second ship. The light hits aloft the second ship at the height of 90 feet, and later on, as it travels towards, or sideways, not towards, but anyway, it travels in a sideways direction like this until the light of the lighthouse hits the bridge at the 23.9 mile mark. So this is a direct representation to scale. If we go to the lighthouse first, you see from the lighthouse we have a few straight lines coming out, and these straight lines are directed towards the ship here and the ship here. There's a red, a green and an orange line. As we can see here, both the green and the orange lines dip below the surface of the Earth. So a straight light will not reach the ships. It will actually impact the surface of the Earth and not reach the ships. And we see these two straight lines come behind the horizon and re-emerge here. The green re-emerges here and the orange re-emerges here, which is impossible. Straight light will never reach these two ships. So what I've done is I've drawn an extra red line, a straight line coming from the lighthouse to the horizon to point B here. This is the only line that is able to bypass the curvature of the Earth and hit the top of ship B. But this is not how it happened in the video. In the video, at point B, which is 23.9 miles away from the lighthouse, at this point the light was able to hit the bridge. This is not what happens here. In our diagram we can see clearly that no light is going to hit the bridge. The only light that's going to pass is going to be over the ship. So let's go to point C. Point C is 26.3 miles away. Here we see that all light rays are impossible. The orange light is seen, but of course it has to pass through the Earth to reach here. It's impossible. The red light is an impossible line also, because it will never hit aloft. So at point C we see that there's no light coming to this ship. So the example is impossible with straight light. So straight light is only for school kids. In order for you to learn trigonometry, the convex globe Earth model points to atmospheric refraction as the reason for the failure of this example of straight light. It is futile trying to make scale diagrams with straight light on a global sphere model. So for all intents and purposes, for example navigation, targeting, etc., the Navy is happy with their approximations in their tables. Straight light is only for school kids. It doesn't work on a sphere. So we have the same situation here, but on a flat earth. We have the lighthouse, the horizon, and the two ships. I began by drawing a line coming from the horizon. It's this blue line coming to the ship at point B and hitting it at the bridge. And I extended this line and I forced it to hit aloft. So in order to do that, I had to bend the light ray upwards by 0.07 degrees. So a straight line from the horizon to the bridge at B and then aloft at C is not possible. The light has to bend upwards in order to do that. No straight line is going to hit aloft from the horizon to the bridge to point C. It's not possible. This guideline is a straight line. It's a dotted blue line. If we follow it to point C, it will hit aloft. However, it's not passing from the bridge, it's passing a bit further up. So there's no straight line, that will hit both places as noted in the video. However, let us help out the flat earth theory by assuming that when the lookout went aloft at point C, the light from the lighthouse was already visible in order to be flexible. So for this purpose, I exaggerated the objects, but the relative dimensions and the distances are exactly the same. This will help out instead of zooming in and zooming out all the time. So in this example, I drew a straight line from the horizon straight through the bridge, and I let the line extend to wherever point that point C is gonna hit. So when the lookout went aloft, the light was already visible. It wasn't just starting to be visible, it was already there. In the video, the ship was actually moving sideways and not straight towards the lighthouse. But let's assume that the ship is traveling towards the lighthouse. When the ship reaches the horizon mark, the light from the lighthouse should now be visible above 15 feet, because the Navy considers 15 feet the elevation at the horizon. So the whole lighthouse will not become visible until much later. As the Bowditch Naval Manual specifies, when an observer is at the horizon, at a 15 feet elevation, that's where he can see the lighthouse at the 15.4 nautical mile distance and at 180 feet height. Because if he is any further away from the horizon, he will not be able to see the light anymore. He will have to increase his elevation in order to see the light again. At 180 feet, the horizon should be at 15.4 nautical miles away. So the ship should be able to see the lighthouse anywhere from 15 feet up to any height. So from here onwards towards the lighthouse, the ship should be able to see something like this. If you use binoculars, you should be able to see something like that. The light from the lighthouse slowly emerging up above the horizon. From the lighthouse, you will be able to see a ship also emerging up above the horizon. Back here, the view from the ship will be either a whole light or a loom or no light at all, depending on the height of the observer. If you're on the bridge, you should be able to see a light. If you're below the bridge, you will see no light. If you're somewhere further back, you may see a loom, something like that. It's like a dispersion of light, because you can't see the actual light, you see its reflection when it's dispersing up into the atmosphere. And from the lighthouse, depending on how far away the ship is, we should be able to see parts of the ship rising up behind the horizon, because that's the description that we get from the Navy. The Navy says below the bridge there is no light. Above the bridge there is light. This is what observation tells us from the Navy. At some point you see the light. A few minutes before it wasn't there. Now if the ship progresses and comes closer to the lighthouse, say at 8.5 nautical miles, what's the view from the ship going to be like? It's going to be something like this. You should be able to see the whole lighthouse and its light coming up from an elevated position, and you can easily measure an elevation angle to that light. You can take your sextant and measure the angle, which should be positive. From the lighthouse you can clearly see a ship approaching now, and still if you get closer you can see that the elevation angle increases, and the same with the view from the lighthouse. You can see the ship increasing in size. Now what do you think? If we put an observer at the lighthouse with a big telescope, do you think he's going to be able to see the ship that is missing? Do you think if we use a telescope we can remove the obstruction and see the ship, the whole ship, the parts of the ship that are missing? And what do you think if we equip an observer on the ship with a big telescope? Do you think he's going to be able to see anything? Do you think he's going to be able to see the lighthouse? If they are above the light line, the dotted yellow line, of course they will be able to see something. We have observers there that testify to seeing the light, also aloft at point C. But if we are under this line, if we are, for example, on the bridge at point C, do you think we will be able to see the lighthouse? Telescopes placed below the yellow dotted line will never see the light from the lighthouse. For example, point B. Please do not think that the light from the lighthouse is weak, and this is why we cannot see below the yellow line. Remember that the light is strong enough to reach 2.4 kilometers further back to point C. So it is not a weakness of light, but rather an angle of light pushing it upwards, further up, the further away we get. So telescopes do not help us here. It's height that will help us here. We need elevation in order to see the light from the lighthouse. However, if we place a telescope in the right place to be able to gather light from the section above, then we will be fooled into thinking that the light is visible in the dark section. We must be careful not to make this mistake. The whole lens of the telescope must be below the yellow line for this experiment to be honest. So something is happening here at the event horizon. There's an event happening. Something is forcing the water between the ships and the lighthouse. Either the earth is bulging upwards into the light rays, or the light rays are bending downwards towards the water. It's one or the other. There is no other explanation for what is going on here. So we have the law of perspective on the left side from the horizon towards the light source, where elevation angles of the light source seem to increase as we get closer to the light source, and we have the law of something else going on the right side of the horizon. So if we draw straight lines indicating the straight light paths from the light source to each part of the ship, to the bridge, to the bridge, to the bridge, and aloft, we see that the light rays, all of them, have positive elevation angles. They're all above sea level, as we see here. So we have the bridge and we have the observer aloft. The distances from the light source and the elevations of each point. The angles, as calculated, are as follows: 0.049, 0.032. Even though they're very close to level, they're clearly positive and above the water level 0. So the angle of light elevation for each point is positive, and it's bigger than the angle of horizon elevation, which should be negative. If the captain at the bridge, for example, wanted to look at the horizon, he will look downwards. If he wanted to look at the lighthouse, he will look upwards. Even at a small angle, it's still measurable. So let's imagine we have 3 ships. One sitting at H and the other 2 at B and C. You can clearly see that the red light rays that reach points B and C pass directly above the ship at H. So what would it look like from the bridge at B if we were to look straight out the window? It would look something like this. We would see a ship standing at the horizon and a light from a light source passing above the ship at the horizon. But this is not what we see, what we observe. In the video it clearly states that the captain at the bridge just about managed to see the light at the edge of the horizon, not above. The same with the observer aloft. So something is happening here at the event horizon that's pushing the light rays down to the base of the ship at H.
Also from this table, he finds the distance of visibility for 55 feet, the height of eye of the Savannah Bridge, to be 8.5 miles.
So remember, the captain at the bridge of ship B can just about see 15.74 kilometers or 8.5 nautical miles. So the ship at H will be just exiting his line of sight. It will be just at the limit of exiting his visibility range. So it will be just sitting on the horizon. So how come the light rays from the lighthouse are passing above it? They should be passing below it, below its base. It's impossible. Although strong enough to reach aloft point C, why can't the light reach the decks of B and C if it's coming from above? If it's coming from above, it should be able to illuminate the whole ship, both B and C. So isn't light obeying its law of straight lines? I thought light was traveling in straight lines. Why isn't straight light obeying basic light rules, like illuminating the whole ship? Why are these ships half bathed in light and half bathed in darkness? What's causing this if light is traveling in straight lines on a flat Earth? I wonder, what is the angle of elevation at B and C? As we said, the angles of elevation are positive. And this doesn't make sense. This is illogical. This is not what we observe, what the Navy observes on a day-to-day basis. This is to scale. This is the horizon, the ship at the horizon, and we see that the 2 red lines are passing above the ship, and they're going to point B. One is going to point B hitting the bridge, and the other one is going to point C, hitting aloft. And we see that in the scale diagram, both red lines that are hitting the proper places are passing above the ship. This is impossible. This is not what we observe. The observer aloft reported the light appearing on the horizon. The captain at the bridge at point B reported the light just about making its appearance on the horizon, not passing at 110 feet above the horizon. This is not what they reported. So there's something else going on. Something is happening at the event horizon. Something is forcing the water to either be raised up and touching the light, or something is causing the light to bend down and touch the surface of the water. There's no two ways about this. We cannot escape this. So light is coming from above the horizon and actually from above the ship at H. So the question remains, although strong enough to reach aloft point C, why can't the light reach the decks of B and C? What law is ruling this side? We know this side is perspective, but what is going on behind the horizon? What's going on here? This is what we have to find out. Even though we don't have data as far as the elevation angle of the light as viewed from B and C, we can be sure that it appears right on the edge of the horizon, not up there, because, as the video stated, they had a persevering lookout.
Note that Hog Island light was sighted by a persevering lookout using binoculars.
And as they stated, the captain at the bridge saw the light when it became visible, not after 10 minutes. So the light appeared on the horizon. There's no point having lookouts. There's no point having a bridge looking for a light in order to navigate at night and seeing it 10 minutes later. They saw it as soon as it appeared on the horizon. And if they both saw the same light, it means the lines of the light should line up, because they're seeing the same light rays just about reaching them. However, as we see from our diagram, these two red lines, they don't line up. They have a huge difference between them. They should be lining up with the yellow line, so that the lookout aloft with his binoculars and the captain at the bridge with his binoculars are seeing the same thing as soon as it becomes visible. I hope you're following me. If we have two ships instead of one, and we have one lookout there and one lookout at the bridge here, and they raise their heads up above the yellow line, they can see the same thing. The same light ray is hitting both of them. However, these lines, they're different. They can be seen here, here, there, there. The red lines are not a reflection of reality, of what has been observed. So the lookout aloft at C and the bridge at B do not line up, and they should. They should line up with the red light rays coming from the lighthouse. Furthermore, as I stated earlier, the ship at H is sitting right bang on the horizon of ship B. Therefore, the bottom of ship H also doesn't line up with the red light rays. The red light rays should be at its base. So we have a problem here. To reconcile the problem, something has to bend. It's either going to be the light that will bend, like this, for example, flat earth theory and curved light, or it will be the earth that will bend, for example, convex, as we all know it from school, or concave models, or light and the earth. Both the light and the earth have to bend. For example, concave model. There is no other option. So in conclusion, I have to say that flat earth theory cannot work with straight light. One thing is for sure, light bends in the flat earth theory. There is no other way. So the law here that governs the side behind the horizon is the law of bending. Is the law of bending of light or the law of bending of the earth. Flat earth theory cannot work with straight light. And now that light bends, then the view from the ship is correct. We see the light on the edge of the horizon. And so the bottom of ship H will begin to disappear as it moves further away until it disappears completely from the view of ship B. It will slowly start to disappear as it moves further away. In the same way as if we start doing a reverse from ship B, if we start our engines in reverse, the light from the lighthouse will also start to disappear. It's simple. So the horizon is called an event horizon because an event is taking place there. And the event in the flat earth theory, if the earth is flat, the event that's happening here is light bending. That forces the light to bend down towards the earth. This could be because light is naturally designed that way, that it has a natural curvature.